Hello, Teresa. Good morning. Hope you're well, staying warm, not going crazy. It's about the best we can do right now. I'm trying to do the same. Play with the cat occasionally. Yes, I know that we don't have school on Monday. And to be honest, Teresa, I don't know. I got to check my email. You know what, Teresa? While we're all breaking in, let me check my email and I'll see if the school wrote yet, okay? With details about next week. And then I'll know and you'll know. Let's see if anybody wrote. The Berlin Senat sometimes likes to decide on Friday afternoon. I hope they don't wait that long. Okay, so here we go. No, 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 no. Okay, so the short answer, Teresa, is they haven't sent me anything yet about next week. I'm assuming we're still going to be online. The latest I heard is when students start to come back to schools, it may well be the younger kids first, the Kitas and the Grundschule. If that's the case, you and I will be online for a while. On the other hand, our crazy Berlin education person, pardon me, I think she's nuts, wanted 11th and 12th graders back a few weeks ago. So I think we better just wait and see what's going on. I'm sure the school will tell all of us. I hope the Berlin Senat decides before Friday afternoon at 5 o'clock, which is what they did last time. Pardon my criticism. So that's a long answer to a short question. Okay, let's see if I got anybody else out there this morning. Anybody else say hello so I know who you are? It's hard to plan, isn't it? As students and as teachers too. But as students, I think it's hard to plan when you don't know what you're going to be doing when. I'd love to have you guys back in school because there's so many demos I want to show you. I may have to make a video in school, but some of the demos I need somebody to help me. It's hard to do it with one person. I'll see. Maybe I can grab Mr. Blessman to help me with a demo or two. Okay. Yeah, I got somebody else here. Who else is here? Ellie, good morning. That's great. And I see I got someone else too. And it's Anne-Sophie, welcome. I'm 3 out of 4. Let's see if we get Zach. And then I have my totally complete physicist. Right. Yeah, anyway, here's a question while we're waiting for Zach. How are you three doing? What do you do to reduce your stress in this bizarre time? What do you do at home to reduce your stress? Yeah, that may well be, Teresa. They certainly require a lot of attention when they're at home. You guys don't require so much attention. Yeah, so any ideas? What do you guys do to reduce your stress? I go outside in the cold or I play with the cat. Zumba, meditation, good. Oh, that's cool. That's a lot of good stuff. Yeah, that's a lot of good stuff, Anne Sophie. Yeah, that'll keep you from going crazy. Yeah, that's really good. I wish I had a craft like sewing. Yeah. I do some music, but I don't do that often enough anymore. Oh, and the dog. You got a dog. That's nice. Ah, and Zach is here. Super. Good morning, Zach. Zach just asking everybody what they do to keep from going crazy. That's okay, Zach. I'm going to check everybody in with a quick check. Check. Yeah, long walks helps too. Yeah. Anybody else got any secrets to Staying sane in the corona time. Okay, then let's begin. What I want to do today, folks, is just review interference with you briefly, and then we'll talk about the Doppler effect. Okay, the Doppler effect. We don't have class, we don't have school next Monday, just as a reminder. And I probably won't have class tomorrow because I'm going to assign some problems instead. And they kind of told us for a lot of our classes that we don't need to meet every single hour if we give an assignment. Oh, writing is good too. Writing is good. I write songs, but not often enough anymore. Okay, so I hope a lot of you got a chance, or all of you got a chance to look at the quick video I sent you of interference pattern with waves. They did these two wave things in the water, and they got a pattern, if you looked at it like this, similar to what we had last time. You know what I mean? And like every other spot was smooth water and really bumpy water. High highs and low lows. So my question to you is, just to warm up everybody, the smooth water was probably where what was located. Remember, the processes are constructive and destructive interference, but what was located at the smooth water? The actual physical thing is called a what at the smooth water. What was located at the smooth water? Or at each smooth water line, I should say. There was one here, 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 here. Each smooth water line was a what? Look back at your vocabulary from last time. Ah, good. Thank you, Ellie. It's a node. So each smooth water line is a node. Remember, that's like no movement. A crest hit a trough there. And so it's smoothed out. They like cancel each other out. The process is negative or destructive interference, but the spot's called a node. Good. And so then the bumpy water lines, each of those is a what, everybody? The bumpy water lines, each of those is an thank you, Aunt Sophie. Each of those is an antinode. So we got antinodes interspersed with nodes. Now, this doesn't just happen with water. It happens with light, it happens with sound, it happens really with any waves where I've got two sources interfering with each other. So this was, again, an interference pattern that I had you draw for the assignment, and that I hope you've gotten that far. If you haven't, do it. And then that's also in the video that's showing that interference pattern with water. And they might show one with light too. I may do that with a video for you at school that I'll make. Okay. Any questions on either of the assignments I gave you? Are you okay so far? Because we're going to then bump into something new for this period. All good? As good as we can be in Corona time? Let me know if you got a question. I'm going to erase this now. Okay, I want to talk about the Doppler effect. And I'm going to do it with a train. And the good thing about you and I is we live in a country, Germany, with lots of trains. So I want you to imagine like a ICE, okay, a really fast train, and it's cruising along here. So here we go. There it is. And there's the track. And there's the train. There's a track going further on. So this thing's really hauling, right? Okay. Let's say we got like a woman driving the train. She's the engineer, and let's say that she's blowing the horn. So she's blowing the horn on the train. I want to show some waves coming out from this. So we're going to talk about Doppler effect first. Example with sound waves. Now we're also going to put a couple other people in the picture. We're going to put a guy out here standing by the tracks, not on the tracks, but by the tracks. And we're going to put a lady back here. She'll be hanging out here by the tracks where the train has gone. Okay? So now let's draw the waves. Okay? So the waves are the sound waves from the honking. Okay, from the train's honker. Oh man, I've been in Germany too long. Horn, thank you. From the horn, the waves from the horn of the train are going out like this. At a constant wavelength. So let's say those are between the crests, or sorry, the compressions, okay? Because it's a compressional wave. So there's some compressions coming out that way. There's some coming out this way. I'm trying to make them the same distance apart, okay? Which is why I'm kind of going sort of slow here. Let's see if any of you are familiar with the Doppler effect. What are the waves going to do out here when I draw them? So this person's going to experience the waves differently, and they really are different. What do the waves do? The train is going this way. So what happens to the waves out here in front of the train? This person will still hear the horn. However, what will the waves do? Can you describe how I'm going to like complete the semicircles going out front, but I've got to change something. Let's see if you've had this before. What do the waves do in front of the train? You still there? Yeah, you're still there. No guesses? Can I give you a hint? Okay, you've heard this. Oh, here we go. You're Wi-Fi. Okay, you're back. Good. All right, Zach, thank you. Will it be closer together because the train is moving forwards? Yes, Zach. That's exactly what's going to happen. So instead of being that far apart, right, I'm going to draw them closer. So check this out. I'm really overemphasizing it maybe, but you get the idea. So that this person's going to hear and this guy's going to say, oh, that's a fairly frequency. So they'll hear a frequency. If the waves are closer together, will this person hear a or a frequency? What do you think, the person out front, based on what Zach said? And now I'll give you my hint. Ready? So you've heard this before, haven't you? Thank you, Ellie. Exactly. So when it's approaching, because they're closer together, like Zach guessed, and now you can probably guess what the person in back's going to hear too. So the waves are going to hit this person more frequently, right? Because there's more more compressions hitting this person. Oh, so they hear a ee, and this person in back, well, these suckers are going to be the opposite, aren't they? They're going to be all stretched out. So they're going to be further apart. I'm going to really emphasize it here more than it would be in real life, but you get the idea. Oh, I should have kept it equal in length, but I didn't because I'm a bad teacher. Okay, so here we go. So she back here, she's going to say, oh, no, that's a fairly low frequency. And the lady driving, she's going to say, no, it's normal because she's right there at the source, right? So that's a normal frequency for her. So this is a Doppler effect, folks. And let's see if you got any questions about it so far. No? Okay. It happens in one of two situations. And I wish we were in a classroom, then I could do this like with drama. If the source, okay, so her honking the horn is the source. If the source is moving towards an observer or away from an observer, you get a Doppler effect. Turns out if the observer is moving, it also matters. What if this guy was running towards the wave, right? If the observer is moving towards the wave, they'll also get them more frequently. So the motion of the observer matters too. Like if she was running really fast, she would cut the Doppler effect because she would be hitting them more frequently. On the other hand, if this lady moved and ran away from the train, she would make it even lower because the waves would be hitting her even less frequently, the compressions. Isn't that kind of wild? So Doppler effect is, as a definition, ready? So it's a change in frequency, and it's a real change. You've all heard it, right? When an ambulance, or do 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 do, right? When something goes by, it goes to a lower pitch. This is why. So now you know something kind of cool. So it's the change in pitch, or we say in physics, in frequency, due to the motion of the source and or the observer. Yeah, that's it. That's it. And let's see, I'll pause, see if you got any questions before we do some math with it. So we're going to learn how to use the Doppler effect, which is kind of a cool thing. And we'll do a little problem with it. I think I'm going to do one with my famous crow and sparrow, where you can see how terrible my bird drawing skills are. But any questions first? All right? Okay, cool. All right, so here we go. I got to make a little board space. I'll leave the definition for a sec down there. Okay, here's the equation. And it's this, the frequency of the observer, let's see. Yeah, I'm going to define these later. The frequency of the observer, you know what, and I'm also going to pull this up. It's one of those equations that I've taught 30 times, and I always want to make sure I teach it correctly. And I did not. Yeah, I did. Yeah, perceived frequency. Good. Okay, so the frequency of the observer, I'll put OBS, equals the frequency of the source. I'll just write it out. Times this big fraction, okay? The big fraction is the velocity of sound plus the velocity of the observer. Divided by the velocity of sound minus the velocity of the source. Okay, all these velocities are in meters per second. We're going to assume the velocity of sound is at like 25 degrees. Turns out sound, the velocity changes when you have a different temperature, but you don't need to know that for this. If we get back to school ever, I got a cool lab for you guys to do, and we'll have to measure the temperature to get the exact velocity of sound in the room. But I really can't think of a good way to do that without you. At any rate, so let's kind of talk here. So the observer, the source. Okay, so I want you to assume the velocity of sound is equal to 340 meters per second. If you're not told in the problem. So I'll say if not stated. And we're going to do a problem with this right now. Okay? Hey, there goes the green. Okie dokie, let's do the famous crow chasing the sparrow. Or do we want the sparrow chasing the crow? Maybe we want a bat chasing a bug. Do we want that? I don't know. Example. A crow at 4.00 meters per second chases a sparrow going 6.00 meters per second. And the question is, what sound does the sparrow hear? What frequency does the sparrow hear? Oh, okay, sorry. Crow calls at 90.0 hertz, which is fairly low. What frequency does the sparrow hear? Whoops, kind of ran those words together. Let me read that in case you can't see it so well. So a crow at 4.00 meters per second chases a sparrow going 6 meters per second. The crow calls at 90 hertz. What frequency does the sparrow hear? Okay, I like to draw these because otherwise I find them kind of confusing at times. So we're just going to draw a crow here. So here we go. There's my crow, and it's going 4.00 meters per second. And here's the sparrow. and it's moving along at 6.00 meters per second. That's the drawing. Okay, let's use the formula and plug some stuff in now, okay? All right, so here we go. I got our formula here. I'm going to write it again. I want to write in shorthand and then use it. So maybe I'll write it over here, okay? So velocity of observer, OB, equals the velocity of the source, time, frequency. Okay, so the frequency of the observer equals the frequency of source times the velocity of sound minus v of the observer divided by the velocity of sound plus v of the source. Okay. I need a little more room. That's why I'm doing this. Okay, we're going to then plug this in here underneath our picture. Okay, so what you and I got to think about is the sign. That's why I'm kind of going slow here. Okay, this is the source, right? Okay, so it's going out and it's hitting the sparrow. So this guy's the source, and the sparrow here is the observer, whether it wants to be or not. So it's hearing the call of the crow. Okay, that's a crow. I better write it because it doesn't look like a crow at all. Okay, so there we go. Because the crow is flying towards the sparrow, should the 4.00 meters be positive or negative? What do you think? Take a gut level guess. The crow is traveling towards the sparrow. Should the 4 meters per second be positive or negative? Yeah, good gut level guess, Ellie. It increases the effect if you go towards something. So it's going to be a positive 4.00 meters per second. Well, now, thank you. All right, everybody's got it. Good. Yeah, and you're all right. Well, what about this guy? This guy's going away from the crow. So what will that do to the effect? Should I make the 6 meters per second positive or negative? It's going away from the crow. Therefore, it would be, I know you all know. I'll just wait for one answer. Thanks, everybody, for participating. All 4 of you. That would be 100% participation. We love that as a teacher. Okay. Yeah, thank you. So it should be negative because it's going away from that, so it decreases the effect. Okay, let's put it in the formula. Ready? Okay, so frequency of the observer, we don't know that. That's the sparrow, so that's our unknown. So F of observer, we don't know. The frequency of the source, we got it. It's 90, right? 90 hertz. Then we got to multiply times this thing. Okay, if we don't know, we're going to call it 342, right? The velocity of sound. So I got a big fraction. So 342 meters per second divided by 342 meters per second. And then I got minus on top, minus the observer. Ooh, now we got to be careful, right? Check this out. So it's minus the velocity of the observer, but that was minus as well. So you know what? I got to go minus a minus 6. You know what I'm saying? And you know what that's going to do to the signs. I don't have to tell you that. Okay, and see why that's so important? Okay, for the other one, it's the velocity of sound plus the velocity of the source. Okay, and that's positive anyway, so I got to go plus 4.00 meters per second. Hoo-ha! Okay, grab a calculator, or go grab one if you don't have one, and go ahead and do that, could you? We can do some of it on our head. 342 minus a negative, so plus 6. So you can essentially just do this, right? 340, what, 8 divided by 338? And then get an answer times 90 and let me know what you get. So punch it in, please, round it, and let me know what you get for a final answer. Let's compare and see what we got. 342 is something, Aunt Sophia, I got to give you. The speed of sound at room temperature is about 342 meters per second. So you just got to trust me on that one. It varies with temperature, but at room temperature, that's about the speed. So that number I have to give you, kind of like the speed of light. I have to just give you that number. It's a constant, light is, and in a vacuum, and sound is a constant per temperature. So let's assume that's what it actually is. Okay, punch it out. Let me know what you get, everybody, and let's see if we agree on the answer. What does the sparrow hear? Here's our sparrow. Our spots. Okay, waiting for your answer once you have it typed in there. $905. This is 90.0, Ellie, so it should be something in the neighborhood of that. It shouldn't be probably 900 and something. That'd be an awful lot. I don't think the effect would be that much. So punch it out again, and others, let me know what you get when you get that far. Let me know what you get, others, because I got something a little different. That seemed kind of big. Pull up a calculator on the internet if you don't have one in your hand, but you can certainly do that. 90.5 hertz. Really? Oh, yeah. Oh, yeah. Did I screw something up? Let's see. So the perceived frequency the perceived frequency, so observer equals the actual frequency times the. Well, my people, yeah, I screwed up. I've given you the answer. I've given you the equation, and I got the signs wrong. It's a good thing I checked this stuff. My gosh, it's so hard to get good teachers. Okay, so here's what it should be. The perceived frequency equals the actual frequency times the velocity of sound. This should be a plus on top, plus the velocity of the observer. I know, I'm so sorry. And the bottom should be the speed of sound minus the velocity of the source. Ugh. All right, let's try it again. Golly. Okay, so velocity of the sound plus that of the observer. So this is going to be 342 plus a negative 6. And at the bottom, it's going to be 342 minus 4. Could you punch that out again? I'm so sorry about that. Please correct your formulas. Or if you forget, look it up on the internet. You'll see the Doppler formula. But it should be via sound plus the velocity of the observer divided by via sound minus the velocity of the source. Good gosh. This is why I have my book open when I do it. How embarrassing. That's life. That's life. Okay. You'll see why I knew it was the wrong answer in a second. All right. So punch it out again. Let me know what you get. And I'm going to act it out with the crow. There's the crow and the sparrow. Yeah, okay, that sounds better. Thank you. Okay, so I got, let's see if others verify it. Teresa did too. Good, thank you. Nice labeling too, everybody. So it should be less than 90, 89.5 hertz. Not a lot less, but slightly less. Slightly less. Now let's see why I knew it was the wrong answer. And you'll figure it out too when you do so. Okay, so here they go, right? Who's faster? Well, the sparrow is. So watch this. Ah, ah, ah. But you know what? The sparrow is increasing the distance. And you see why then? If I go, ah, 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 but it's moving away faster than yeah. So the sound waves, the compressions are going to be spreading out more because it's increasing the distance, the sparrow is, between itself and the crow. Kind of like that. I know I'm overemphasizing it, but you get the idea. So they're spread apart more, the waves. So they'll hit the sparrow less frequently. So I knew it needed to be less than 90. So that answer looks way better. That's, in fact, the correct answer. Okay, and let's see if that answers Ellie's question too. Yeah, okay, Ellie, you said exactly the same thing. Exactly right. Thank you. Thank you. That's perfect. Good. Okay, after that hullabaloo and me giving you the wrong formula, that is now the Doppler formula, and that's the right way to do it. By the way, there's a cool thing, because we're complete physics, I want to comment on where you find this also with light. Because it's really neat, okay? So the Doppler effect with light I put it as a question mark, and the answer is, of course, yes. Turns out the light from many stars apostrophe after the S, is shifted to the red side of the spectrum. Now, you and I, that won't make any sense until we study more with light, which we will. So just bear with me. Shifted to red side. If you know colors, it's the red side of Roy G. Biv. But if you don't, we'll learn that another point in the course. So many stars' light is shifted to the red side, indicating movement away from Earth. What theory did this allow astronomers to come up with? So the stars are shifted red, indicating movement away from Earth. Not all stars, but a lot of them. They're moving away from Earth. This allowed astronomers to come up with a very famous theory about the universe. What is that theory? All of you should get this, actually. That's why I love total physics, because we can kind of go into other side things, which are so cool. So what's the theory that this gives well, proof for. Hint, TV show. Yeah, and Sophie, the Big Bang Theory. So this is evidence for the Big Bang Theory. And so if you think about it, what that means is if you got a lot of stars and you got Earth here, I'll put Earth in blue. We're not at the center of the universe, believe it or not. And if most of the stars are going away from us, how can I show that? I'll put little arrows. I know we're not in the center of the universe, but some are going towards us. What that theory is then that the theory is that they all started from a single point in the center where there was an explosion. So there's the Big Bang Theory right there. Bang, 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 bang. And in milliseconds, they spread out and they keep spreading out. So that when we see the light from those distant stars, it's moving away from us. So we don't see the light exactly the right frequency. Like folks in chemistry know that when we have electrons moving back and forth, they give off light in a certain frequency. But that light is shifted a little bit because the star is moving as it gives off that light. So it's shifted a little bit to a longer wavelength, so a smaller frequency or lower number frequency, and that's the redshift. Okay, that's what it's called in science, the redshift. So it means they're moving mainly away from us, and because of that Doppler effect with light, we grew the Big Bang Theory. Oh, if they're all moving away from us, there must have been, or most of us, then from the center of the universe, there must have been a big bang, and that made the stars continue as they're doing today. Most of them are still moving away from the center of the universe. Isn't that kind of a fun fact and a nice use of the Doppler effect, right? Or a nice place that we see it, which people didn't expect it, by the way. Yeah, exactly. There you go. See, you know the song already, so you're actually all set with that. Yeah, good. Fun, huh? Okay, yeah, good. Waves are great. There's so many fun applications of waves. I'm going to try and do a demo at school. I think I told you that with Mr. Blessman on standing waves, but I can't even really talk about that now. There's not much sense till you see it. So we're going to move right from here. Let me tell you about the course. Okay, so we've had a little bit about waves in general. We're going to talk now about sound waves for the rest of this period, and then do some more with sound. We'll talk more about light probably in 2 or 3 different chapters. Light is complicated and it's cool. So we're going to give light a fair amount of time in this course because it's so flippin' important. But for now, we're going to talk about sound. Okay? So unless there's further questions from you, I'm going to erase this and continue to talk about sound a bit. If that sounds okay. All right. Okay. See the stuff you learn from watching a teacher on a YouTube video? Oh, life is crazy, I tell you. Okay, so let's see what I want to show you. Let's talk about humans, okay? Here, oh, sorry, sound. That's our more or less our chapter, okay? Humans here about 20 hertz up to about 20,000 hertz. It varies a little person to person, okay? You guys are definitely going to hear higher frequencies than I do. I'm already losing my hearing, as do most adults, but my family particularly. Okay, so what if it's less than 20 hertz? Or it's a sound that's greater than 20,000 hertz? I'm going to give you the first one, see if you can guess the second. If it's less than 20, we call it infrasonic. Infrasonic. You've heard of like infrared. Infrared. Well, this is infrasonic. And infrared is a lower frequency, like we just had with the red Doppler shift. And infrasonic is a lower frequency of sound than humans can hear. So infrasonic, if it's less than 20 hertz, it's infrasonic. What if it's greater than 20,000? Can you guess the name? Sonic. If it's higher than 20,000, we call it sonic sound. We also have the same one. Oh, Teresa, she's on fire. She's got it already. It is indeed ultrasonic. With light, we have ultraviolet. Whoops, forgot my L. Don't want to get the L out of there. I do it to keep myself amused. Sorry. Okay, so there's ultraviolet light, which has a much higher frequency than we can see. And this is ultrasonic sound, which has a higher frequency than we can hear. It's a different type of wave, of course. This is a compressional wave. Light's a transverse wave. But still, just for grins, because it's fun, what critters can hear infrasonic? And what critters can hear ultrasonic? So give me an animal that you think you know and tell me if it hears higher frequencies than humans or lower frequencies than humans can hear. Okay? So let's see if you probably know some. Usually my students know some cool facts about that. So give me a critter and tell me, oh, this can hear higher. Yeah, birds. Which way? What can birds hear? Kind of depends a little on the bird, but generally. Dogs can hear ultrasonic. Yes, Ellie. So I'll put dogs over here. You can buy a dog whistle that you can't hear, but the dog can, and its ears will go up. And some birds can hear ultrasonic. Good. Some birds. Yes. True, Teresa. Any others you guys know? There's a really important one, which we're going to do an assignment on, which also hears ultrasonic. Yeah, thanks, Anne-Sophie. Bats. Bats hear ultrasonic sound. And that, I think, is an assignment I'm going to have you work on next week because it's pretty cool. Bats are interesting critters. When I worked in Kentucky years ago at Mammoth Cave National Park, I used to have this woman named Tony who worked at the gift shop, and she would say, "Them bats is ugly. I hate them bats. Them bats is ugly." She had the most terrible Kentucky accent. Anyway, that's a long story. So what about infrasonic? Do you know any things that hear really deep tones, lower tones than you and I can hear? Yeah, rhinos, good. Rhinos hear infrasonic. So rhinoceri. I think that's the plural. Let's hope it is. Who else hears infrasonic? I got to think how to say that every time. Whales. Teresa. That is such an important one. Get this. Whales not only send infrasonic sound, but they can send it a long distance. Okay? Like they found whales singing a song off the coast of England, and minutes later they heard whales pick it up and sing the same song back off the coast of North Carolina. So they can hear through the water several thousand kilometers. How fun is that? Okay, rhinoceros, whales, and there's another land creature that can hear infrasonic as well. You don't have it yet. It's elephants, and they can hear many kilometers. Elephants, not elements. They can hear many kilometers through the earth. So the wave goes through the earth. That's the medium, and they can pick it up and hear it from kilometers away, and more or less speak with each other and hear a message from other elephants, which is pretty cool too. Okay, question here from Teresa. You can only hear the low with a special device, right? Exactly, Teresa. I can hear the low or the high sounds if I have a special recording device to allow me to do that. It will take the infra or ultrasonic sound and change it into a sound you can hear, but it has to do that mechanically, electronically, so it's changed so the human ear can pick it up. Or you can watch it on a screen if you have a microphone that will pick that up. Giraffes. Okay, dolphins too. Dolphins for which ones, Zach? And giraffes for which ones? I don't know giraffes. Do you know that, Anne-Sophie? Because I don't really know if they're probably, but I don't know. I won't put them there unless you know that for sure. But dolphins for sure belong in which ones, Zach? Yeah, I think mice do too. Mice, probably rats. And Zach, what about the dolphins? Which one do you want it under? They actually use this to hunt, kind of like bats. Ultrasonic, exactly. So, dolphins, that's a biggie there. When we get to the chapter on interference patterns, we're going to talk about how dolphins hunt, and it's pretty cool. Okay? All right. You probably guessed the answer to this question, but what sounds carried further? What sounds carry further? And I've kind of already told you, haven't I? These go a long way, so the ultrasonic ones. Whoops. Sorry, wrong word. The infrasonic ones. Turns out, because these are so frequently, the ultrasonic, the waves are so frequent that they break up easier. Isn't that wild? So these guys, so high frequency, it's the same with light, by the way. High frequency waves break up easier because the crest and troughs or compressions, if it's sound, because there's so many of them, it doesn't really seem to travel very well. So high frequency waves break up easier than low frequency. And you know this already, right? You ever be in the city and you hear somebody's like bass from their stereo? You don't hear the treble, right? Because the treble's all broken up. But you hear that bass, man, because the bass travels easier because it's a longer wavelength or a lower frequency sound. Yeah, so you know that, don't you? Okay, let's see your other comments. Sorry I talk so much. Anne-Sophie says giraffes belong to infrasonic, so I'll put giraffes under here too. Good. Crickets, yeah, let's say a lot of insects do. I don't know about all, but some insects. Good. Yeah, so infrasonic sounds carry further. And that's why, right? Because the compressions are further apart, so they get broken up less easily than the ultrasonic ones. Okay? Ooh, far out. Yeah, so that's kind of something fun. Again, we'll do a activity with bats. Yeah, I think I'll have that for next week. I got to think about what I want to do with you. Yeah, because that's kind of a neat one. Okay, let's go on. And some other stuff we should know about sound. Sound, it transmits faster in solids than gases or liquids, for that matter. It has to do with the density of the molecules. So it's sort of like in air, they got to like touch each other. They got to carry the compression through the air, but they got to move to hit each other. If you have a solid and you talk through a solid, right? You ever do this with a piece of string with somebody? If you talk through a solid, it actually very quickly, much quicker, conveys the compressional wave across through the solid because the molecules are much denser. So denser equals faster sound movement. A couple of the sound facts. Sound is, let me get this right, 1/10,000,000th the speed of light. So sound seems like it's fast, but you know what? It's ain't nothing, right? Speed of light is really fast. So that's why, of course, first we see the lightning during a storm, then the much slower wave, then we hear the thunder. Just common sense. Beautiful common sense. Should we give you that rule? The rule is if you count for like 3 seconds, it's a kilometer away. So it's the 3-second rule. So if I see lightning, and it takes it so 6 seconds to reach me. That would be then 2 kilometers away. So it's about 3 seconds per kilometer, or if you like miles, about 5 seconds a mile. Now this sounds corny, but I've used this. Just laying awake in bed. If you're in bed and you hear a storm, you can hear it storm get coming, because what'll happen is you'll see lightning and then you'll wait, and then there's the thunder, and then you'll see lightning and maybe the thunder is then sooner, and then you'll see lightning and then the thunder is even sooner, And if you see lightning and hear the thunder at the same time, stay in bed. Okay. Or if you hear the time period getting longer, you know the storm is going away from you. Not fun. Just by hearing, you can use the 3-second rule to judge how far a storm is away from you. Let's see if you have other things here. Alligators are infrasonic as well. Cool. Thank you, Teresa. Good research. Unfortunately, I erased that already, but add it to your list. Crocodiles also, right. And the infrasonic range. How about that? Low fish. Low fish. Beautiful. Okay, my people, we're going to continue next time, and that will probably be next week. Let's see. So I don't see you Monday, so I assume I see you Tuesday. So I'll either meet with you at school or I'll send you a video to watch on Tuesday. I don't know how I'm going to do that yet because I want to show you a demo I can't do at home here. Okay. So that's it. I'm going to send you a couple of Doppler problems to do. Not a lot, but I'll send you a few in an assignment and have a reasonable amount of time for you to do it. I think we're good to go. Thanks, everybody. And I'll see a couple of you later on in AP Chem. For everybody else, have a good weekend. I'll see you next week, which will be Tuesday, I think.